We are changing a bit our geography and from Germany switching over to France. Institut LAUE-LANGEVIN, or ILL, is a service facility. Its purpose is to provide the international scientific community with, first one, the brightest possible beams of neutrons, the state-of-the-art of scientific instruments, and the expertise of its scientists, engineers, and technicians. And most of its neutron beams are used in ILL to probe materials, and the fields of investigation range from technology applications to biology and health. So my pleasure is to give the floor to Giovanna Fragneto, professor in ILL. Giovanna, the floor is yours.
Thank you very much. Thank you for the invitation. Thank you for the introduction. So as we said, well, we are not only moving country, we are also moving to another kind of tool that is used for studying structure of matters, and this is neutron scattering. So I'm going to talk to you about the Institut LAUE-LANGEVIN. Is an international research center based around the nuclear reactor, where we produce high fluxes of neutrons to study the structure and the dynamics of matter. So I've been working there in the last 24 years, and I've been leading the large scale structures group for the last 6 years. And my main scientific interest revolves around the structure of membranes. Now, I said it's an international research center. It is indeed funded by mainly 3 countries, which are France, Germany, and the United Kingdom. And then there is a contribution from a number of other countries, European countries, smaller contribution. And the use of the facility really is proportional, is nearly proportional to the support, to the input of these different countries to the facility. Although there are ways to use the facility, even if one is not partner country. And if you are interested in this, I can tell you more about it later on. Right. So we said the ILL is in France. It's actually in the French Alps, in a town called Grenoble, a town very popular with lovers of skiing, of ski resorts, but also a town which possesses a very high concentration of scientific infrastructure. We have universities, we have public research centers, many companies, and many international research centers, mainly located in the EPN campus, the European Photon Neutron campus, including the European Molecular Biology Laboratory, the European Synchrotron Radiation Facility, the Institute of Structural Biology, and the ILL. And between these institutes, there are a number of partnerships that help users collaborate and using the various tools that we have on campus in a complementary way. And notably, the partnership for structural biology and for soft condensed matter have been rather successful in the last few years. So neutron scattering is, together we have heard about electron lasers, synchrotron radiation this morning. We have microscopy. It's one of the, belongs to one of these European leading infrastructures for characterizing materials. In Europe, we have about 10 major neutron sources. Then there are about 6 in North America, 5 in Asia, and Oceania. And neutrons, I will show to you how it is really complementary to these other methods, and how can be a unique, irreplaceable probe for studying structure and dynamics of materials. The ILL, the reactor of the ILL went critical in 1972. So it's been working for nearly 50 years. Neutrons were discovered by Chadwick back in the 30s, and then over a few decades, more and more sophisticated ways were found to produce fluxes of neutron beams. And since 1972, the ILL remains the highest flux reactor. We have a few more facilities that have come up after that, but we remain as the highest flux reactor in the world. Then in the 70s, also past sources started to develop. We have at the moment the most powerful are based in the UK and United States, and are ISIS and SNS. And we heard this morning that very soon the European spallation source will come online. So it will be a very high brilliance source, much higher brilliance source than the ILL, although the average flux is going to be similar. So the ILL will remain competitive and will remain competitive and complementary with ESS when this will come online. And indeed, we have strong collaborations with people at ESS to help and to make sure that the facility comes online in the most successful way. Okay, so the ILL reactor, a neutron source that generates about 5 to 10 to the 18 fast neutrons per second, has a maximum power of 58 megawatt. So neutrons are produced by fission, and the material that we use is enriched uranium. So for each neutrons that starts the fission reaction, 2.5 neutrons are produced, and one of them is used to continue the reaction, and the other one is then collected and used for sending it to instruments for doing the experiments. So neutrons are extracted, are moderated, so their energy, they are slowed down, the energy is reduced, and they are sent to neutron guides, where by reflection, they can be delivered to the instruments. Before arriving to the instruments, their energy is selected, their wavelength is selected. They may be polarized. We will see that neutrons have a spin. Their size is defined. They interact with the sample, and then their energy or their direction is varied. And by studying this variation in their energy or in their direction, we can get detailed information on either the structure or the dynamics of the material under study. So here is a top view of the facility. In the reactor dome, we have the reactor core where neutrons are produced. And then we have guide halls where a suite of about 40 instruments are located. So 28 ILL instruments, and then we have a certain number of instruments which are collaborations with partners institutes all over Europe, and that we call CRGs. The instruments, according to the way they work, they are divided in different groups. So we have a diffraction group, a large-scale structure group, nuclear and particle physics group, and the spectroscopy group where dynamics is studied. According to what one wants to see, the instruments will have different optics, different detectors, different collimations, but overall, in all all experiments will follow a very simple path of having a flux of neutrons, an energy filter, so something that will select the energy or the wavelength, interaction with a sample, and detection over a detector. So they are basically, the basic components are always the same. And regarding science done at the ILL, is mainly dominated, of course, by physics. There is a lot of work done on magnetism. We will see that the neutron has a spin, so it's very interesting for magnetic studies. there's a nuclear and particle physics. But neutrons have also some very special features that make them extremely interesting for soft matter or biological studies. So we will see that, I mean, about 1/3 of the use of the ILL is for soft matter and life science studies. And yeah, the variety of systems that can be studied is very large. We have more and more work devoted to material science. I will tell you at the end of the talk that we are now finally offering some imaging facilities for material studies. So why are neutrons so interesting, and what makes them different and complementary to other tools, especially X-rays? So neutrons are electrically neutral, so they can penetrate deeply into matter, and they do not damage the studied sample. So they are very sensitive to plastic components because they are very sensitive to hydrogens, and so we can image material in a complementary way with respect to X-rays. The fact that they can penetrate deeply into matter allows the use of very sophisticated sample environments. So we do measurements applying all sorts of external fields. We do measurements very high temperatures, very low temperatures, so high pressures, systems under shear. So we use in situ techniques, and the fact that they do not destroy the sample is obviously very interesting and very precious for biological material or soft matter material. We can do in operando in situ and in operando studies as well. And this is just an image of an engine in action. Then, as I said, the neutrons have a spin, therefore a sensitivity to magnetic properties. We can polarize neutrons and characterize all sorts of exotic materials, materials with complex structures, and materials with complex behavior. Very popular these days is work done on these magnetic structures called skyrmions. The wavelengths of neutrons are comparable to atomic sizes. We can, so we have wavelengths that go from the fraction of angstrom for thermal neutrons up to tens of angstroms for cold neutrons and more without neutrons. So we can probe complex structures with sizes of the order of thousands and more of nanometers, as well as we can go down to fractions of the angstroms for looking at interatomic distances. And we do play with the wavelengths of neutrons, so by slowing them down in what we call cold sources or hot sources or moderators. And finally, why they are so popular for soft and biological material. As it has already been said, neutrons interact with nuclei, contrarily to X-rays that interact with the electrons. And if we look at the scattering power of neutrons and X-rays, while in the case of X-rays, it will increase monotonically with the number of electrons in an atom, so will be larger and larger as bigger and bigger is the atom. In the case of neutrons, the scattering power varies randomly in the table of elements, and we have the special feature of having a different scattering from different isotopes of the same element. And this is very much exploited for the case of hydrogen and deuterium, where the scattering is very different. And by isotopic substitution in soft matter or in biological systems, we are capable of highlighting parts of the systems of interest and we can remove completely scattering for other parts of the system. And this is a particularly unique feature. Example, I have couple of pictures here to give you examples. Here, for example, we can see that we can study low resolution structures of proteins in solutions that are stabilized by lipids nanodiscs. We can make these nanodiscs transparent to neutrons, so we can match them out with the surrounding solution and have signal coming only from the protein inside. Similarly, for the case of polyelectrolyte surfactant complexes, this is some work that came out recently where structure and dynamics was studied. We can get this complex, immerse it in solutions that can match either the surfactant core or the polymer part, the polyelectrolyte part, and then have signal coming only from these parts of the system and study in detail only that part of the system. Or finally, in the case of layered systems, so systems that make layers on a surface, one could study the moving of material from one layer to the other by using this isotopic substitution and changing in this way the composition of the layer as the molecules move from one layer to the other. So the structure of biological soft matter is proved at the ILL by the group to which I belong, which is the large scale structure group that contains small angle scattering machines for studies in solutions, reflectometers for studies on surfaces, small angle diffractometers. Dynamics, on the other hand, is studied by neutron spectroscopy. So with large-scale structure instruments, we study structures that go from the angstrom to several hundreds of angstroms. With dynamics, one can study motions from the femtosecond nanoscale time scale to the 100 nanoseconds time scale, using inelastic scattering, backscattering, and spin echo instruments. When we welcome users, we have facilities that can to help them preparing the samples. So in soft matter, for example, we have set up a partnership for soft condensed matter that will offer a number of equipment for sample preparation, delicate sample preparation, as well as complementary characterization during neutron experiments. And for example, within this sort of partnership, there's a development of specific systems. There is a very big program around model membrane studies, and I'm particularly attached to it, where what we offer are ways to properly prepare samples that will have shapes different according to the technique that one wants to use and according to the information one wants to get. So we can provide help to prepare this sample and study them with large-scale structures techniques. And just to give you an example, within this partnership, we've been working in recent weeks on COVID-related science, as has been requested by the management, and there is a big effort in all facilities for getting an understanding on what happens and how to help in fighting COVID-19. So one of the examples we've been working on has been looking at the interaction, as I said, at the angstrom scale, of small peptides, fusion peptides that are a part of the spike protein, that is this red protein that you see when you have the image of coronavirus, as well as the interaction of the entire protein with membranes that contain a receptor in the membrane capable of attracting the virus and then starting the process of internalization. So we used the surface studies to have a look at that. The analysis is in progress, but already we are capable of having some preliminary results about removal of lipids from the membrane, as well as the structure of the attached membrane to the S receptor. Another technique that is going to be used, has been already actually used in the United States for COVID, but is a technique used for many other things as well, is crystallography from proteins. So what makes this technique interesting and complementary to X-rays is the fact that with neutrons we are sensitive to protons that you cannot see with X-rays. Hydrogen bonding, hydrogens that you don't see very well with X-rays, hydration. So basically what we do when we do our measurements, and the ILL, we do it using a LAUE diffraction instrument. We start from a structure coming from X-rays, and we are capable of putting the hydrogens into the structure and localizing hydrogen bonding or water of hydration. So there's work going on in the case of COVID. We are not doing it, this will come next cycle at the ILL, but we have a long history of working on systems involving viruses, in particular in collaboration with our USA colleagues. People here have been working on the inhibition on drugs that inhibit the enzyme protease, that is an essential enzyme in the life cycle of HIV, and is a clinical drug target. So with neutron studies, it has been possible to identify precisely how these different inhibitors link to the protein, and it has been able to suggest different ways to enhance the binding or limit the drug resistance. We are moving more and more towards exploiting fully the complementarity of X-rays and neutrons, and we are acquiring in-house X-ray equipment. So for example, now for a single crystal diffraction, so either from protein or more generally from all crystals, we do have an X-ray diffractometer that allows you to measure exactly the same sample with neutrons and X-rays, and that can be accessed when you have a neutron experiment. Similarly, thanks to the collaboration with the LAUE-LANGEVIN University in Germany, and thanks to a BMBF grant, we have acquired a SAX machine that we have installed in perpendicularly to a SANS instrument, allowing us to do simultaneously small angle neutron and X-rays scattering. So here you will see this, I've lost my mouse, the sample position. You will have your sample tilted at 45 degrees, allowing to hit the same spot with X-rays and neutrons that are oriented perpendicularly one to each other. A first paper, so this instrument is, this facility is not yet available to users, but will be very soon in the next year, hoping that we can run properly, but it has been commissioned, and this is already a paper that has come out this year in the Journal of Applied Crystallography, where the growing of gold colloidal nanoparticles stabilized by a surfactant, surfactant micelles, has been followed. So these data have been collected simultaneously. With time, we see the increase of the SAX signal due to the growth of the nanoparticle, but a decrease of the SANS signal coming from the surfactant micelle. And this observation helps understanding the polydispersity of the gold nanoparticles, as well as the way they grow, and what's the influence of this stabilizer of this surfactant. And finally, another example where we use simultaneously neutrons and X-rays is imaging. So we have a new instrument called NEXT, an instrument that allows to get to 3 micron resolution, collect 1 millisecond images or 1 second tomography. And that allows to image a number of interesting things. So we have a paper that's come out recently on the localization of water in the roots of plants. But a lot of work is done on batteries. And here again, we have a paper that has come out this year on simultaneous studies of neutrons and X-rays of real lithium manganese oxidized manganese oxide batteries, and the detailed structure has been possible with X-rays, but the diffusion of lithium is a small element, but is strongly scattered by neutrons are strongly scattered by lithium, so it has been possible to see the lithium diffusion with neutrons. And there are many, many more examples, but in 20 minutes, we cannot cover much. So I leave you with this summary containing some numbers about the ILL. So 50 years of work, 21,000 publications, about 600 per year. 120,000 visitors, 40,000 experiments. So the countries that contribute are again displayed here. But we have users that come from 45 different countries, and there are different ways to access if one is not a member not from a member country of the ILL. And then we have some modalities for applying beam time, but I can tell you more details if you're interested. So thank you very much for your attention.
Thank you very much, Giovanna. And we have a couple of questions, in fact, coming in. And one of the questions is, what is approximate waiting time for from application until delivery of research? Maybe you can speak a bit on timetable.
So when one talks about delivery or research, you mean publication, or you mean when you do the experiments? Anyway, well, I'll give you some ideas. So we have 2 rounds of proposals submission per year. So every 6 months, one can submit a proposal. From the time the proposal is submitted to the time the beam time is awarded, unless there are special reasons, and one, if you have really very hot science, you can go for some direct or discretionary time, or this sort of, some fast lanes, but normally would be at least 6 months from when you submit a proposal to when you can do an experiment. So starting from those 6 months in that year, you do the experiment. And then depending on the difficulty of the experiment, from there to publication, there is an average of 2 years. Sometimes if you have a neutron diffraction pattern from some powder where you can index very quickly your diffraction peaks, you publish in a much faster way. If you have some complex spin echo experiment, it may take much longer. So depends. But it's very similar to what you would find at synchrotron facilities, actually.
Mm-hmm. Thank you. So similar path in all facilities. The next question is, which are dominant industries that are approaching ILL at a particular moment, or in more human way, the question would be, who are the most interested in neutron scattering?
Okay, that's interesting. There are maybe people in the audience who know better than me the answer. So I am familiar with industries from companies that become interested in for soft matter, so for surfactants, polymers. So you would have companies like Procter & Gamble, Unilever, these sorts of industries interested in polymers or surfactants are very good customers. We have a little bit of pharmaceutical industries, but not so much, and industry of petrol. Yeah, I mean, I don't know, and of course engineering. Of course, we do have companies that come here for engineering. I expect that the imaging machine is being just offered for public use. Already it has had some industrial users, but I expect that the imaging is going to be more used, so for batteries, materials, cements, and so on.
Okay, thank you. Thank you very much for extremely interesting presentation and answers. Giovanna from France, ILL.